first speaker is Krastin Nikov from the University of Bristol. He's going to talk about power modeling of heterogeneous embedded systems.
Thank you. Hello everyone, so my name is Chris, and so I'm going to talk more about power modeling. I'm a graduate of the University of Bristol. I did my undergrad course there, and now I'm continuing my PhD there as well. So my main area of interest is computer architecture, and how that particularly is relevant to this is that I'm sponsored by a company called ARM, who are based in Cambridge. Has anyone else heard of ARM? All right. So as you know, they're quite a large semiconductor company. They're very dominant in the mobile market, and that's where I come in with my research. So first, let's start off with what is heterogeneous computing. It's basically the idea of using more than one processing unit to do type of computing. So a very common example is a PC, which has a graphics processing unit, so that whole system with the main CPU and the GPU is also heterogeneous computing. In my particular area of interest, in mobile systems, which is what ARM specializes in, they've currently developed a heterogeneous computing system for CPUs, which is called Big Little, and it features four small power efficient cores and four large performance oriented cores. So for example, the Cortex A15 is a large core, and the Cortex A7 is a small core, and they're usually featured in clusters like this, group of four. So it's a multi-core system. Why it is particularly relevant to this day and age is, so there's an emerging problem of dark silicon, which is basically as devices become smaller and smaller, there's more and more power and heat dissipation, and currently the devices are small, so we can't really power up the entire device at the same time, otherwise it dissipates too much heat, and we need bigger and bigger cooling systems. And in mobile space, this is a bigger and bigger problem because phones will become hotter and hotter. So one way to tackle this problem is heterogeneous computing. However, that's just the hardware side of things. It's more complicated on the software side, because we need advanced energy management solutions. So just having the ability to schedule tasks on a big or a small core, whether they require more or less performance, is a big task on its own. So the currently developed solution that's running Linux, which is what Android's running on, which is what's running on most mobile devices that use ARM chips, just uses your utility thresholds, and there's not much further information about power. And what I'm aiming to do is develop power models and make that an extension to the current software management solutions to enable more intelligent power management on these devices. So what I'm trying to do is build a hybrid power model that could be usable at runtime to predict the power usage of an application for a specific time slot, and then maybe decide to migrate it to the more power efficient cluster or remain it on the performance cluster. So depending on how much power it's predicting it's going to use. So the way I'm doing that is I call it hybrid, because I'm using 3 different types of components to help me predict the power. I'm using voltage, temperature, and frequency information. I'm using also a component called performance monitoring unit, which has information, which is used in most modern CPUs, and has information about the number of instructions, the cache misses that are typical to software execution. And the third component I'm using is CPU states, which I can extract information for how much time the CPU has spent in idle or servicing input-output requests or stuff like that. So what I'm restricted by is the number of these events that I could use. So I need to keep my model relatively small so I can be used in real time. I can't just use a million of these because it would make it harder to compute. So how I'm doing that is I'm using a linear regression with ordinary least squares. So what I'm doing is I'm running a workload generating a bunch of data points which all store the sensor information and all other information about the CPU and the power, and I'm trying to map these data points onto the power, and that results in an equation which then for future data points that I didn't train the model on can be used to predict the power consumption just based on that information. So at the moment this is my current methodology. I'm running a collection script which runs my workloads, collecting all the events, then I'm analyzing them, finding out the best small set of events that predict the best power, the power of the closest. Then I'm building a power model based on those events, and finally I'm testing the power model on a test set that is completely different from the one that I used to train the model on. Right. So what's integral to my research is having the ability to actually run the workload and monitor power at the same time, so I can train the model. Fortunately, as of recently, there have been systems developed for Big Little that have power sensors in them, so I can use them as a training platform. That's exactly what I've used. This is hard kernel Odroid XU3. I don't have on me to show because my supervisor forbade me to endanger the board, but this is what I'm currently working on. So it features a Samsung Exynos 5422 SoC. So it's the same picture that I've used previously with 4 big Cortex A15 cores and 4 small Cortex A7 cores. It is the chip, I believe, is featured on the S5, Samsung Galaxy S5. Yeah, so the best thing about it is that it has power sensors. Unfortunately, I can't use real smartphones to do my research on because they don't have any of these power sensors, and getting the power L information from them is quite complicated because they're really small connections. So you need special stuff to do that. All right, so what I currently developed, so I've developed a model each for the big and the small core. So the difference between the Cortex A15 and the A7 isn't just like the Cortex A7 just being a scaled down version. There's also different architectural features. The A7 has a smaller pipeline, and so it's not very trivial to model both. So we need a model for each of them separately. Right, so my first attempt was to build a model on the entire range of frequencies available for the CPU. And as you can see, that didn't perform quite well because there's quite a lot of difference for each frequency for the events that I was monitoring. So then I decided to build models for every frequency level. And as you can see, so this generates just one equation, and this is 18 equations, but it performs much better. So my idea is to use these in sort of a lookup table type of structure, and then build that with the scheduler. All right, and these are my models built for the Cortex A7. Yeah, top one is on the full frequency range, bottom one is per frequency. The A7, because it's a much simpler core and it has a much lower power dynamic range, the model performs much better on the same set of events. So that's good. All right. So as a summary, so this is compared to all the other literature out there, this is a pretty novel methodology of combining all 3 types of events, the physical and then the PMU events, and the CPU state. And I achieved relatively good accuracy, 8% and 5% on the A7 and 8% on the A15. So my next step is to try and integrate this into a real-time scheduler and try to see if I actually achieve any reduction in power. Right, so this work, it's going to be presented in a conference pretty soon. So I'm really looking forward to that. Yeah, that's it for now.
Now we'll take some questions.
Yes?
Yeah, I've got one. Is there any sort of user-friendly software platform, if we can call it as user-friendly, to actually access sort of the power of these microchips and use
No.
this for any computation?
So I've scripted everything. So there's no methodology to read the sensors and then do the analysis on them. So I've just scripted everything. I've scripted all the reading from the different event types. And then I store those in files, and I use Octave, sort of read through the files and do the mathematical analysis of that.
Can you talk about real-time analysis of the events?
Yes. So in order to do that, we need to keep the granularity relatively. So I can't sample the events very fast, otherwise we will have quite a lot of overhead. So I do sample them at half a second, and as we can see, it achieves relatively high accuracy as well. So I've also used other sampling frequencies, just the one that I presented now, it's just the one. Yes.
So by using different frequencies every time for your analysis, don't you think that it should be better if you consider your analysis on a resolution level? Say, on a resolution level you have a whole curve, and then you don't predict a single point, a particular event, but rather you have a whole mathematical curve for events.
I didn't follow you, but sorry.
Okay, so what do you mean by frequency?
So the CPU, I can clock it at different frequencies.
Right.
So at every frequency level has quite different power dynamics. So that's what I'm getting at with
So
I've built.
for example, a curve from one frequency level would look or would have different mathematical statistical properties than a curve on another frequency
True,
level.
yes.
And then you could try to utilize this information into your analysis, and rather than using simple wireless, you could input the time or the resolution component in your analysis. But I'll talk to you later about it.
Okay, thanks. Any other questions?
I've got a question. So my question is, whether you treat the CPU as a black box, essentially, you set the frequency, you run it, and then you take your measurements, or you're aware of what's inside, what's going on, and you try to mimic it with your model.
So that's a good question. Currently, CPU architectures are very complex, so you can't just have a one equation like simulating everything like you could in the past. You can't do that anymore, it's just too complicated. So using machine learning is sort of the best approach we have at the moment to generate these equations. Other works have used mechanistic information like pipeline depth, and the number of execution units and stuff like that, but I've opted not to use that. Specifically because I want to make my methodology transferable to other architectures. So ARM are coming up with, well, the next big little, which is 64-bit. So I want to try that in a few months. And I think this methodology would be much more reproducible on that one if I started more mechanistic information. But if this accuracy does not prove good enough for using a real-time scheduler, then I also have that option.
Any further questions? Let's say Krastin.